And today we are diving into scientific history to address those individuals who were, well, tragically relegated to footnotes regardless of their monumental work.
Exactly. Our source material points directly to a painful recurring trend known in historical science studies as the Matilda effect.
That's the core thesis we need to unpack. The Matilda effect is, it's the phenomenon describing the bias against acknowledging the achievements of women scientists.
Right.
Their work is often overlooked, minimized, or most painfully directly attributed to their male colleagues.
And our sources are so clear that this wasn't just, random bad luck.
No, not at all. It was a pervasive systemic issue. And what's perhaps most striking is that this bias persisted even during periods where these women had to overcome immense societal hurdles. I mean, lacking equal education, professional opportunities, just to get into the lab in the first place.
It makes you wonder how much more quickly science would have advanced if those barriers just hadn't existed. The sheer grit required to make a foundational discovery, only to have it quietly erased once it proved successful, it's heartbreaking.
It really is.
The objective of this deep dive, as laid out in the sources, is vital. We need to retell and share these stories repeatedly until these names, the true architects, become household names.
For the groundbreaking contributions they made, we're talking about inventions and insights that literally formed the bedrock of the 21st century.
Spanning what fields?
Everything. Genetics, geography, climate modeling, compute, you name it.
So let's start with a foundational area where the name associated with the discovery has become almost interchangeable with modern biology itself: the structure of DNA. Okay, let's unpack this, starting with the double helix. Every high school student learns the names James D. Watson and Francis H.C. Crick.
Right, they're the famous duo.
They're credited with uncovering the double helix structure of DNA, which is fundamental to all human genetics. But the critical experimentalist, the true hero here, is Rosalind Franklin.
Franklin was an absolutely brilliant British physical chemist, and her specialty was X-ray crystallography, which, it's important to understand just how difficult that is.
It's not just taking a picture, is it?
Not at all. It's an incredibly intricate process. You're shining these intense X-ray beams through crystallized materials, in this case DNA fibers, and then you record the diffraction pattern on photographic film.
And analyzing that pattern is more like interpreting shadows than seeing an object?
Precisely.
Yeah.
You have to deduce the shape from how the X-rays scatter, and her dedication to improving the quality of her DNA samples and the precision of her camera setup was just unmatched.
Which led to the breakthrough image.
Yes. The sources confirm that in 1951, she produced the absolute cornerstone of the double helix discovery, the stunningly clear diffraction pattern known to history as Photo 51.
And that was taken by her graduate student under her direct supervision, right? Raymond Gosling.
That's right. And this image showed an unmistakable X pattern.
And for any crystallographer, what did that X pattern immediately signal?
That X was definitive proof of a helical or a spiral structure. It was the smoking gun.
So not a ladder, not a block, a spiral.
Exactly. And not just that. The density of the pattern, the spacing of the marks, suggested the molecule was composed of two strands. A double helix, with the bases stacked horizontally in the center. She had the data. She was meticulously calculating the dimensions of that helix.
And here is where the institutional and, frankly, personal credit controversy just flares up. It's a perfect illustration of the Matilda effect in action.
Yes. Franklin's colleague at King's, Maurice Wilkins, while she was away from the lab, and the historical accounts on the level of betrayal do vary a bit, he showed Photo 51 directly to James Watson.
Without her knowledge or consent.
Without her informed, explicit consent. And Watson saw that X, and by his own later admission, he understood the structure almost instantly. That critical visual evidence was the final missing piece of the puzzle for him and Crick.
Because they were working mostly on theoretical models, right? They were building physical models, trying to make the pieces fit.
Correct. They didn't have the hard experimental data to confirm their structure. Photo 51 was that confirmation. It was the key.
So they took that visual key, and suddenly their model was complete.
Exactly. Watson and Crick published their structure findings in the journal Nature in April 1953. And this is the really painful part.
The placement of her paper.
Yes. Franklin's detailed paper on the structure followed immediately after in the same journal. It was placed third in the sequence. And that placement, unfortunately, made her work appear merely supportive of their conclusion, rather than the foundational evidence used to derive it.
It frames her as confirming their genius, not enabling it.
That's a perfect way to put it. The timing afterward is particularly poignant and just devastating for historical recognition.
It truly is. Franklin continued her phenomenal work, but she was struck by ovarian cancer and passed away in 1958 at the tragically young age of 37.
So young.
And 4 years after her death, Watson, Crick, and Wilkins received the Nobel Prize for the double helix discovery.
And because Nobel Prizes are not awarded posthumously, her exclusion was cemented, formally removing her from the most prestigious recognition possible for this defining moment of modern science.
But it's so important to remember that her genius wasn't just limited to this one iconic image. She was an engine of scientific progress across multiple fields.
Oh, absolutely. Her PhD work was highly impactful during a critical time. She meticulously unraveled the structure and porosity of coal.
Coal. That seems like a big jump from DNA.
It does, but it was vital. That research, performed during wartime, directly informed the British effort to develop more effective carbon filters for gas masks used during World War II. Her work literally helped save lives. And later, she moved to Birkbeck College, where her work on the structures of RNA and viruses, specifically the tobacco mosaic virus, was foundational. It directly supported Nobel laureate Aaron Klug's later success in creating 3D images of viruses.
So her career spans war efforts, fundamental biology, and virology, all marked by the same meticulous precision.
Exactly. She was just a brilliant, rigorous scientist, period.
We just saw how Franklin's work helped the war effort. Now let's pivot from the laboratory to the planet itself, where another foundational scientist was looking at global heat Eunice Foote.
Eunice Foote is arguably one of the most unjustly overlooked figures in modern climate science. If you ask any contemporary scientist who discovered the mechanism behind the greenhouse effect,
The process by which Earth's atmosphere retains heat.
they will almost certainly cite the British scientist John Tyndall.
But our sources state unequivocally that Foote, an American scientist, inventor, and a prominent activist in the women's rights movement, first theorized and experimentally demonstrated this effect a full 3 years before Tyndall's recognized work.
Her methodology, executed in the 1850s, was elegant in its simplicity and just pioneering in its scope.
So what did she actually do?
She utilized a series of experiments involving glass cylinders equipped with thermometers. The core idea was to test how different concentrations of atmospheric gases reacted to solar radiation.
What gases was she testing?
She filled the cylinders with various components: moist air, dry air, and crucially, carbon dioxide, which she referred to by its older name, carbonic acid gas.
And then just put them in the sun.
Placed them out in the sun and carefully measured the weight and magnitude of the temperature changes inside each one.
And what was the defining result that pointed to modern climate science?
She found that the cylinder containing carbon dioxide reached the highest temperature, and it retained that heat for longer compared to any other gas she tested. This was a profound, world-changing observation.
Which led her to theorize the global implication. She connected her little experiment to the entire planet.
Yes. She wasn't content just to document the lab result. She explicitly hypothesized that variations in atmospheric CO2 levels could explain past warmer periods on Earth.
That challenged the prevailing geological theories of the time.
Completely. The common idea was that Earth was just a fiery ball that was slowly cooling down. Foote suggested an atmospheric component was at play. A contemporary Scientific American article, in fact, praised her work, recognizing that it directly linked carbonic acid gas to those warmer ancient temperatures.
That is the very definition of a foundational discovery. But the institutional barrier she faced is just painful.
Despite publishing her findings in the prestigious American Journal of Science in 1857, the patriarchal structures of the scientific community prevented her from presenting her own research.
She couldn't even stand up and read her own paper.
No. At the major scientific conference, the American Association for the Advancement of Science meeting, she had to ask a male colleague, Professor Joseph Henry of the Smithsonian, to read it on her behalf.
And Henry's presentation was where the dismissal began.
The sources indicate he made these patronizing, gallant remarks about the fact that the paper was from a lady.
Oh, cringe.
Right, but then he characterized the scientific work itself as difficult to interpret, maybe suggesting it wasn't rigorous or just wasn't important.
What a contrast. A popular science magazine gets it, but the head of the scientific body dismisses it.
It's a stark contrast. Foote's insight into the heat-trapping capabilities of CO2 wasn't just an overlooked historical fact. It's the very genesis of our scientific understanding of the modern greenhouse effect and, well, anthropogenic climate change.
Moving now into the world of physics, we encounter a story where political persecution intersected with scientific injustice. It's Meitner. This isn't just a story about scientific credit, it's about survival.
Meitner was an Austrian-Swedish physicist, one of the most brilliant minds in Europe, a student of the legendary Max Planck, and remarkably for the time, she became the first woman to hold a full professorship at a German university in Berlin.
And her initial concept, the key intellectual jump, was fundamental to the later discovery of nuclear fission.
It was. She was the one who suggested that her colleagues, Otto Hahn and Fritz Strassmann, should bombard uranium atoms with neutrons to study how uranium decayed.
And the idea was to make bigger atoms, right?
Exactly. The hypothesis was that you could create transuranic elements heavier than uranium. She laid the intellectual and experimental groundwork for a decade.
She was at the apex of her career, and then the Nazi regime targeted her.
That's right. As an Austrian Jew, even her protected status as a professor vanished after the Anschluss in 1938. She was forced to flee Germany immediately.
With almost nothing.
Just 2 small suitcases. She left her research, her laboratory, her entire life abruptly behind and managed to reach safety in Stockholm.
And her colleagues, Hahn and Strassmann, they continued the experiments.
They did, and they obtained results that were utterly baffling and counterintuitive.
They were finding lighter elements, not heavier ones. They couldn't rationalize the data.
They were completely perplexed. Hahn wrote to Meitner in December 1930, detailing their findings, that they had found barium, an element much, much lighter than uranium, after the neutron bombardment. He called the results absurd.
And that's where Meitner's brilliance, working from exile, provided the critical synthesis. She solved the puzzle that her colleagues in the lab could not.
Correct. Over the Christmas holidays in Sweden, while she was walking with her nephew, fellow physicist Otto Frisch, Meitner used the physical data Hahn sent her. And she and Frisch correctly interpreted the unexpected results as the uranium atom splitting into smaller nuclei.
A process they named.
Frisch suggested they name it fission, after the biological process of cell division.
This realization that the nucleus of an atom could be split, and in the process convert a small amount of mass into immense energy, this is the foundation of everything nuclear.
The shock was profound. Meitner immediately calculated the staggering amount of energy released by this process using Einstein's famous equation E equals mc squared. The concept that mass could be lost and converted into such monumental energy was revolutionary. When they published their paper in 1939, it fundamentally changed physics overnight and launched the nuclear age.
Yet the credit for this defining moment went entirely to her former collaborator.
In 1945, Otto Hahn received the Nobel Prize in Chemistry for the discovery of heavy nuclei fission.
And Lise Meitner.
Entirely omitted. This is one of the starkest examples of the Matilda effect, compounded by political prejudice. The Nobel Committee claimed her work was theoretical and secondary, despite the fact that she was the one who provided the intellectual framework and the physical explanation, the very term fission.
49 nominations for Nobel Prizes in physics and chemistry throughout her career, and she never won. That is just staggering.
It is a dark mark on the Nobel history indeed. However, late in her life, she did receive significant recognition from the United States government. She was awarded the prestigious U.S. Enrico Fermi Award in 1966, an honor she shared alongside Hahn and Strassmann.
So some late recognition at least.
Yes, finally receiving official recognition for her contribution to a discovery that defined the 20th century.
Next, we turn to the First Lady of Physics, Tiansheng Wu, a Chinese immigrant whose work on the subatomic level was so meticulous and definitive that it overturned one of the most bedrock, cherished principles in modern science.
Dr. Wu's background is so key to understanding her tenacity and precision. She was an experimental physicist whose father was a progressive engineer, a huge influence.
He championed women's education.
He did. He ensured she received the same serious academic encouragement as any son, instilling in her a deep value for freedom and equality that fueled her relentless pursuit of truth in the lab.
And her early career demonstrates a unique ability to handle complex, high-stakes experimental environments.
Absolutely. She contributed significantly to the Manhattan Project during World War II. Her expertise in identifying rare isotopes was so renowned that when the B reactor at the Hanford site, the world's first large-scale nuclear reactor, kept shutting down.
It was randomly shutting down.
Frequently. They couldn't figure out why, so she was called in. and she correctly identified a specific xenon isotope as the culprit, a piece of crucial detective work that solved a major wartime engineering crisis and saved the project critical time.
So she had this reputation for almost surgical precision in the lab, especially with dangerous exotic materials.
Exactly. Her reputation for meticulous, high-stakes experimental control was unmatched. She eventually became the first woman to receive tenure in Columbia University's physics department.
Which brings us to 1956.
Right. This is the context when her two colleagues, theoretical physicists Songdao Li and Chenning Yang, approached her. They had hypothesized a fundamental breakdown in physics regarding the process of beta decay.
They were questioning parity conservation. Okay, let's make sure we clearly define parity for the listener, because its violation was world-changing.
Parity conservation, or mirror symmetry, was, until that point, a foundational belief in physics. The idea was simple. The laws of physics should be absolutely identical whether you observe a physical process directly or in a mirror image.
So nature shouldn't have a left or right preference.
Precisely. It was held as true, much like the conservation of momentum or energy. It had been unquestioned for decades.
So Li and Yang theorized this symmetry might break down specifically in the case of the weak force, one of the four fundamental forces of nature. But theory is nothing without proof.
And they needed an almost impossible experiment built to test it, and Dr. Wu delivered.
What did she have to do?
They needed to test the beta decay of cobalt-60. To accurately analyze the direction in which the emitted electrons decayed, they needed the cobalt-60 nuclei to be perfectly aligned in a strong magnetic field.
Which means getting it incredibly cold.
Yes, this required her to design a critical experiment using the radioactive isotope at temperatures near absolute zero, a monumental engineering and physics challenge in itself.
So her expertise in handling dangerous materials like cobalt-60 was why they came to her.
Absolutely. They needed her because she was the only one they trusted to execute such a difficult experiment flawlessly, and the result was revolutionary.
What did she find?
Her experiment proved Li and Yang's theory correct. The weak force violates parity conservation. The particles emitted during beta decay favored one direction over its mirror image.
It overturned a fundamental assumption that had underpinned physics for decades.
And here's where the institutional injustice lands, paralleling the Franklin story. The theory celebrated and the experimental proof sidelined.
Li and Yang won the Nobel Prize in Physics in 1957.
For the theory of parity violation, Dr. Wu, who designed, executed, and delivered the definitive experimental proof upon which the entire finding rested, was entirely omitted.
And they relied on her. They told her not to publish until they had.
They did. It remains one of the most egregious snubs in Nobel history, cited as a clear example of institutional sexism. Her work immediately influenced the development of the Standard Model, our core understanding of particle physics.
And she had a pretty pointed quote about it later.
She did. She later questioned bias by asking, "I wonder whether the tiny atom and the nucleus have any preference for either masculine or feminine treatment."
Shifting gears radically now, let's move from particle physics to connectivity. The modern world runs on Wi-Fi and Bluetooth, and the mind behind the foundational concept for those technologies belongs to a golden age Hollywood actor, Hedy Lamarr.
That juxtaposition is fantastic, isn't it? It perfectly captures the surprise inherent in the Matilda effect. We know the star, but we don't know the engineer.
So Lamarr, an Austrian-born actor, wasn't content with just being a silver screen star.
Not at all. Driven by patriotic desire during World War II, she worked with a composer, George Antheil, to develop a secret communication system.
And the invention was called frequency hopping. Why was that so vital?
It was designed as a radio guidance system for Allied torpedoes. Torpedoes at the time were controlled by steady radio signals, which were really easy for enemies to detect, to jam, or to intercept.
So they needed to make the signal unjammable.
Exactly. They developed a system where the signal rapidly and synchronously hopped between 88 different radio frequencies in a sequence known only to the transmitter and receiver.
So if the enemy tried to jam or track the signal on one frequency,
it would instantly be gone, having moved to the next frequency on the synchronized pattern. It made the signal incredibly difficult to intercept.
it was a spread spectrum communication system.
That's the technical term. The U.S. Navy, however, initially ignored her patent. They deemed it too complicated to implement during wartime.
But the idea didn't die.
No. Her patent was eventually rediscovered by researchers years later, and that core concept, the idea of rapidly changing transmission channels in a pattern, became the foundational basis for modern spread-spectrum communications.
Which includes Wi-Fi,
Wi-Fi, CDMA, which is used in cell phones, and Bluetooth. All of it.
And it took until shortly before her death in 2000 for her to finally win the Electronic Frontier Foundation Award. A profound example of delayed recognition.
And speaking of foundational technology, we can't forget Lady Ada Lovelace, who is widely recognized as the very first computer programmer.
This predates modern electronics entirely. She was the only legitimate daughter of the poet Lord Byron, and she worked closely with the mathematician and inventor Charles Babbage in 1843 on the analytical engine.
And it's important to distinguish Babbage's two machines. The difference engine was basically a calculator, but the analytical engine, that was something else.
That was a theoretical machine capable of generalized computation.
Exactly. Babbage was the creator of the physical design, but Lovelace was the one who saw its full potential.
And she expressed that potential through her detailed notes on the engine,
in which she wrote what we now recognize as the world's first computer program, an algorithm designed to calculate Bernoulli numbers.
But more than that, she conceptualized the core principles of modern computing that went far beyond just number crunching.
Precisely. She detailed the concepts of iterative loops and subroutines. She explicitly theorized that the machine could manipulate any data symbol, not just numbers.
She said it could compose music.
She did. She wrote that if musical notes could be translated into numbers, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. That realization, the universal power of the algorithm, is the foundational insight of modern computing.
So while Babbage invented the hardware, Lovelace invented the software concept.
You could absolutely say that. Her intellectual contribution is profound.
Now we move to medicine and geography, starting with a powerful story of perseverance, public health triumph, and tragic theft. Alice Ball and the injectable leprosy cure.
This is an incredibly important and deeply painful story. Hansen's disease, or leprosy, was intensely stigmatized in the early 20th century. Patients were often condemned to cruel isolation, famously on Molokai Island in Hawaii.
The traditional folk remedy was chomugra oil, but using it was just miserable.
Correct. It tasted foul, it was difficult to absorb through the skin, and critically, it was dangerously impossible to inject directly into the bloodstream because it was an insoluble, viscous oil. It would just cause clots.
Enter Alice Ball, a chemist focused on solving this seemingly intractable problem.
In 1916, at the astonishingly young age of 23, Alice Ball became the first woman and the first black chemistry professor at the University of Hawaii.
And she solved the chomugra oil problem.
She did. She figured out how to chemically manipulate the oil to make it water-soluble and safe for injection.
How did she do that?
She cracked the complex chemistry by identifying the active components, the fatty acids, and then she converted them into water-soluble ethyl esters. This solution allowed the medicine to be safely injected and absorbed, revolutionizing treatment overnight.
The human impact was instantaneous and immense. But the personal tragedy that followed is just heartbreaking.
Just months after her breakthrough, at age 24, Alice Ball died suddenly, possibly due to complications from chlorine gas exposure during a lab demonstration.
And her untimely death paved the way for institutional injustice.
Arthur Dean, the head of her department, took over her work and published it as his own. He seized her research, erased her name entirely, and published the successful injection method, calling it the Dean's method.
He just stole it.
Plain and simple. Thankfully, credit was eventually restored, even if it took decades. A colleague, Harry Holman, later spoke up, intervening in a 1922 paper to document Ball's true role and coining the accurate term. The Ball method.
And the Ball method became the most widely used leprosy treatment for years.
For the entire pre-antibiotic era of the 1920s and 30s, it freed countless people from isolation.
We see a similar pattern of institutional dismissal, though thankfully less fatal, in neuroscience with Candace Pert.
Pert's story is concise but so powerful. While she was only a graduate student at Johns Hopkins, she made a foundational discovery.
She found the opiate receptor.
She discovered the critical receptor in the human brain that allows opiates, both natural endorphins and medicinal drugs, to lock in and modulate pain and emotion. A massive Nobel-worthy breakthrough.
And her reward was immediate professional dismissal.
Her professor, Dr. Solomon Snyder, received the formal recognition and the prestigious award for the discovery. And when Pert protested this clear professional theft of her dissertation work, his response was the deeply cynical line, "That's how the game is played."
Just a devastating dismissal. Now, moving from the microscopic world of receptors to the global scale, let's talk about Gladys West, another one of the hidden figures, whose meticulous mathematical work is now central to modern life.
Gladys West was a mathematician born in 1930 in rural Virginia. She realized that education was her only viable path out of farm or factory labor.
And she became the second Black woman hired at the Naval Surface Warfare Center in 1956.
That's right. She began her career doing these incredibly complex hand calculations before mainframe computers were fully integrated.
And her work focused on analyzing satellite data, right?
Yes. And as computing took center stage, her role shifted to sophisticated programming. She was tasked with analyzing and correcting the computer's output, constantly dealing with their not completely right mistakes.
And her key accomplishment was the creation of an extremely detailed geodetic model of the Earth.
What makes a geodetic model extremely detailed? Why wasn't a simpler model sufficient? Because the Earth is not a perfect sphere. It's an irregular, lumpy shape called a geoid, distorted by gravity and mass distribution. For a global positioning system to work accurately from orbit, you need a model that accounts for all these minute irregularities.
So her work was to create the true mathematical shape of the Earth.
Exactly. It involved massive computational effort to translate complex satellite observation data into the precise, complex mathematical model that accurately defines the three-dimensional shape of Earth relative to its center of mass.
And that mathematical model is the absolute non-negotiable basis for the Global Positioning System, GPS. Without her precise computations, your phone navigation would be useless.
That's right. When asked about her groundbreaking work, she reflected that she wasn't thinking about the future global impact of GPS. She was just focused on the immediate task.
Her quote was, "You're thinking, I've got to get this right."
That meticulous focus on accuracy created a technology that guides cars, ships, and planes worldwide today. She was eventually and rightly recognized with induction into the U.S. Air Force's Space and Missile Pioneers Hall of Fame.
Finally, in this section, let's highlight Nettie Stevens, whose work revealed one of the most basic and fundamental biological truths about heredity.
Nettie Stevens, an American geneticist, definitively discovered that sex is determined by chromosomes. This was a massive paradigm shift. Before her work, scientists often assumed that sex was determined environmentally.
By things like temperature or diet.
Exactly. So she had to provide irrefutable proof of a genetic basis for sex. She studied cell division in the male common mealworm.
Glamorous work.
Very glamorous. But she was extremely meticulous in observing the process of sperm formation, and she successfully identified two physically distinct types of chromosomes in the male mealworm cells.
Ones we now call X and Y.
Yes. She documented the large chromosome, the X, and a conspicuously smaller one, the Y. She noted that eggs fertilized by sperm carrying the X chromosome developed into female mealworms, and eggs fertilized by sperm carrying the Y chromosome developed into male mealworms.
Indisputable evidence that the male parent determines the sex.
It was. Her work was foundational, yet she is rarely mentioned in biology texts that focus solely on the chromosome theory of heredity.
This next section features two women whose contributions were so fundamental to their fields that they were essentially the silent partners in Nobel-winning discoveries. Let's start with Esther Lederberg, whose work defined the golden age of bacterial genetics.
Esther Lederberg was an American microbiologist who defied institutional prejudice from the start. She was told science was too difficult for women. Her entire career is a testament to perseverance and pure brilliance.
She's credited with at least 3 core breakthroughs that reshaped modern molecular biology. Let's start with phage lambda.
In 1949, she discovered phage lambda, a latent temperate virus in E. coli K12. This wasn't just finding a bug. This little virus became one of the most important and versatile tools in molecular genetics.
Because it could insert itself into the host's DNA.
Right. It could pop in and pop back out. Research on phage lambda was crucial for elucidating the operon concept, which explains how genes are regulated and switched on and off in bacteria.
And she also solved the mystery of how bacteria exchange genetic material horizontally.
Yes. While trying to map phage lambda, she discovered the F plasmid, or fertility factor. This is a small circular DNA element that enables bacterial conjugation.
Which is basically bacterial mating.
It is. They transfer genes to each other laterally, which is crucial for adaptation and, importantly, for the spread of antibiotic resistance.
And I remember from the sources that her husband, Joshua Litterberg, initially had a different, incorrect theory about how that exchange happened.
That's right. He thought it required a complete mixing of chromosomes. It was Esther's discovery of the F plasmid that solidified the actual process of horizontal gene transfer.
And finally, a technique that is still absolutely essential in every microbiology lab today, replica plating.
Co-developed with Joshua Litterberg, this technique lets you lift colonies from one culture plate and quickly transfer them to multiple new plates, keeping the exact same spatial arrangement.
And that was crucial for proving
That resistance mutations arise spontaneously before the bacteria are exposed to the antibiotic. A critical piece of evidence for Darwinian natural selection in microorganisms.
So she gave us a key genetic tool, figured out how bacteria evolve, and co-developed the technique to study that evolution. But the Nobel Prize story for her husband is the classic Matilda effect outcome.
Joshua Litterberg won the 1958 Nobel Prize for gene recombination in bacteria, which was entirely dependent on the tools and mechanisms Esther discovered.
And her recognition.
In his acceptance speech, he relegated her input to a brief acknowledgement, thanking many colleagues, above all my wife.
And her later reflection on this is a testament to her quiet defiance.
In a handwritten note, she wrote simply, "No, I did discover the fertility factor. Despite this, her tools remain foundational." And recently, a bacteria species, Jatropha habitans Letterbergiae, was named after her.
A fitting tribute. Moving now to astronomy, Jocelyn Bell Burnell's story is another perfect example where a doctoral student's groundbreaking, painstaking observation led to official recognition solely for her supervisor.
We're talking about the discovery of pulsars. Bell Burnell was a research student at Cambridge working on the immense data flow coming from a massive new radio telescope designed by her advisor, Anthony Hewish.
The scale of the data was staggering. She was analyzing dozens of miles of paper charts per week by hand.
And it was amidst this mind-numbing labor that she noticed the anomaly. She noticed a persistent recurring signal, a tiny bit of scruff, as she called it.
A rapidly pulsating radio source.
So regular, flashing precisely every 1.33 seconds, that Hewish initially dismissed it as man-made interference.
He told her to ignore it.
But she was persistent. That's the recurring theme, isn't it? She persuaded him that the signal was real. After months of checking, they realized this was no man-made signal.
They joked it might be Little Green Man.
They did. But it was, in fact, a neutron star, an incredibly dense, rapidly spinning remnant of a massive star explosion. We now call them pulsars.
And the inevitable Nobel Prize for Physics came in 1974.
It went to her supervisor, Anthony Hewish, and his collaborator, Martin Ryle, controversially omitting Bell Burnell. The debate over whether students should receive the Nobel has centered around her case for decades.
But she offered a very measured, almost institutional defense of the decision.
It is remarkable. She publicly stated she wasn't personally upset, arguing that the supervisor carries the final responsibility and thus should benefit from the successes.
That's incredible self-assessment.
But her later actions speak volumes. In 2018, she received the £2.3 million Special Breakthrough Prize in Fundamental Physics for her achievement.
And she didn't keep a penny.
She donated the entire amount to establish a fund aimed at boosting diversity and supporting disadvantaged students, women, ethnic minorities, and refugees in physics. Her priority was clearly advancing the field, not personal credit.
Looking back at these 12 women, the sheer breadth of their influence is staggering. We've covered fields from the structure of DNA and the definitive origin of the greenhouse effect to nuclear fission, wireless communication, the first computer program, a major leprosy cure, GPS, bacterial genetics, and astrophysics.
They weren't just contributors on the margins, they were the fundamental architects of our modern scientific understanding. Their names should stand alongside the giants of history, not be hidden in footnotes.
Right. If you know Watson Crick, you must know Franklin. If you cite Tyndall, you must cite Foote.
Exactly. And yet, this deep dive shows us that the Matilda effect, the systemic oversight where recognition only goes to men, is surprisingly persistent even today.
Our sources note that this bias continues even as the proportion of women increases at all academic career levels.
This points to a deeper structural problem within the institutions of science, particularly around high-status awards like the Nobel Prize, where the rules limit recipients to 3 individuals.
Which fundamentally conflicts with the collaborative reality of modern research.
Absolutely. Teams can involve dozens or even hundreds of critical contributors, as we saw with the Higgs boson discovery. This rigidity often leaves the primary experimentalist or the junior researcher, who is often a woman out in the cold.
So what does this all mean for you, the learner? Why is recognizing these names today so critical beyond simply honoring these individuals?
Well, I think it's essential for understanding the true collective nature of knowledge production. When we acknowledge that innovative ideas, crucial mathematical models, and definitive experimental skills come from every perspective, not just those traditionally recognized, we gain a much clearer and frankly more inspiring picture of how science actually advances.
It demonstrates that true genius is not confined by gender, politics, or institutional bias.
Even if the rewards often are.
This brings us to a final thought, perhaps the most provocative one from this entire body of source material, centered on the experimental brilliance of Chen-Sheng Wu.
Right. She proved, through the Wu experiment, that nature itself, in the realm of the weak interaction, is fundamentally asymmetrical. It distinguishes between left and right.
The universe is not perfectly symmetrical in its fundamental laws.
Exactly. So if the very laws of the cosmos recognize and depend on a lack of perfect symmetry, why do our human institutions, the committees, the awarding bodies, the history books, continue to insist on a rigid, narrow symmetry in how credit and monumental rewards are distributed?
That institutional insistence on a narrow, traditional narrative is the question we must carry forward as we seek a more accurate and equitable scientific history. An outstanding final thought. The deep dive into the architects of the modern world who became footnotes is complete.
We hope you feel thoroughly informed and armed with the knowledge of these incredible scientific leaders.
We look forward to diving deep into your next stack of sources soon.